Brought to you by the Astro Youth House chapter from STEM Arts Lab, Space on Earth is a student-led podcast that inspires listeners who are curious about space to explore the wonders of the universe through the voices of young thinkers, creators, and dreamers.
Each episode blends personal curiosity with scientific discovery, from the mysterious depths of black holes to the practical impacts of space on Earth, like GPS, climate science, and medicine.
Hosted by STEM Arts students from Taos, New Mexico, this podcast draws connections between space, art, and science, how these things all impact us here on Earth, and their meaning to humanity.
You'll hear raw, insightful conversations about topics like light pollution, the overview effect, lunar exploration, and the societal impact of the space race.
Whether you're into exoplanets, dark energy, or just stargazing from your backyard, Space on Earth makes space personal, accessible, and inspiring. We believe that space isn't just for astronauts and scientists, it's for everyone.
Join us on this adventure as we explore the cosmos from Earth, one story at a time.
Special thanks to the Lore Foundation for helping launch this podcast.
Hello, everybody. Welcome back to another episode of Space on Earth. I'm your host, Wyatt Wade.
And I'm your co-host, Pascal Heitzman.
And today we are talking about astrogeology. Geology is the study of Earth's rocks and basically history written in stone. What about rocks in space? Space rocks like Mars, the moon, asteroids, all that stuff.
So what exactly is astrogeology?
Well, geology is the study of Earth, like its rock history. Yeah. Astrogeology takes those same exact tools and applies them to space, planets, moons, asteroids, comets. Anywhere solid in the solar system is fair game, really.
Okay, so if geo means Earth, astrogeology means star Earth study, is that like a little bit contradictory?
I guess it technically is. The name got coined fast during the space race in the 1960s when NASA actually just needed a word for it. And it stuck pretty well. I mean, in my opinion, it works. Some scientists actually prefer planetary geology for exactly that reason, though. But astrogeology is what most people say.
Okay, so we've talked about what astrogeology is, but what are the kind of questions that astrogeologists or planetary geologists like to answer?
Questions like, how did this planet form? Was there ever water on Mars? Why does our moon look so cratered? What can a rock on an asteroid tell us about the early solar system? And I think like my favorite part about all of this is by studying other worlds. Like, we can learn more about our own planet. Earth is constantly recycling its crust through plate tectonics, which erases our ancient history. But the moon has been geologically quiet for billions of years. It's basically a fossil record of the early solar system just sitting there.
Yeah, that's so cool. It's like we can see all of Earth's geological processes and like the footprints that happen on Earth but get worn away. But on the moon, it stays there. And so we can see that there.
Yeah, exactly that. I've got a question. Who do we actually credit with inventing astrogeology?
Okay, so a geologist named Eugene Shoemaker, who is often called Gene Shoemaker, founded the Astrogeology Science Center, which is a department of the United States Geology Survey in 1963. And he made the argument that geological principles from the Earth could be applied to the moon, and therefore there should be a department that looks into that for future moon landings. At the time, most scientists thought that the moon's craters were volcanic. However, Gene Shoemaker proved that they were from asteroid and comet impacts, a huge shift that kind of changed how we looked at the moon and how it related to the Earth.
Wow. That's really cool. Interesting last name.
After founding the astrogeology research program, He personally trained Apollo astronauts in geology, and he picked actual landing sites on the moon. So he was one of the people who like scoped out our photos of the moon and chose where would be the safest places to land and the places that we could be able to investigate geology on the moon. Later in life, he and his wife Carolyn co-discovered a comet, which was then named Shoemaker-Levy 9. That comet then crashed into Jupiter in 1994, and it's one of the most dramatic astronomical events of the 20th century. He died in 1997, and NASA sent some of his ashes to the moon on the Lunar Prospector, which is really cool. And NASA wanted to recognize all of the work he had done to support NASA and all of his findings about the moon.
Oh, wow, that's really cool. I didn't know that he was on the team to pick out the landing sites. I knew it was in some desert. I think it was like Arizona or something, where all the Apollo astronauts were like testing out their spacesuits like in this desert that was kind of like designed to be like the lunar surface. I didn't know he was a part of that team. That was really cool. Yeah. Is there any connection to his work in New Mexico, or at least around New Mexico, like Arizona, Texas, that general area?
Yeah, there's actually a ton. So the Astrogeology Science Center is based in Flagstaff, Arizona, which is we're in New Mexico, so that's only a state away and literally up the road from some of us. And Flagstaff is chosen for this because the landscape is so geologically useful for space training. There's a lot of similarities. For example, you have the meteor crater nearby, which is a almost perfectly preserved impact crater. You also have the volcanic lava fields and cinder cones that come from the San Francisco volcanic field. NASA also used these like geological features to train the Apollo astronauts on field trips. And why this reminded me, there was actually in the Taos area, there was a lot of training for the Apollo 15 mission, including testing the rover that was used on the moon, as well as field tests so that the astronauts would be able to take accurate geological samples on the moon. And that all happened right up in Taos because it had a very similar geological area as one of the places that they were investigating on the moon, which was the Hadley Ryle, which is a valley on the moon. And it was one of the places that the Apollo 15 mission looked at and took geological samples from. And so they used the Rio Grande Gorge as like a mock or a testing ground for everything that they would then use on the moon, which is super cool because it's like right outside our doors, right in our backyard. And the American Southwest and, of course, New Mexico was essentially like a dress rehearsal for the moon, which is super cool.
Oh, okay. I thought all the Apollo stuff happened in Arizona. I would have remembered if it was in New Mexico. I don't know why I thought Arizona.
Okay, so we've talked about who started the field and some of some of the connections to where we live now. But what did an astrogeologist actually study? What's the actual science? And if you're an astrogeologist, what are you looking at day to day? What's the kind of information and data that you process to create and to conceive of these connections between the Earth and other planets or other moons?
I was wondering the exact same thing when we were researching this episode. They're really just four big areas. First off are impact craters. Almost every solid body in the solar system is covered in them. And by counting and analyzing craters, like craters on our moon, scientists can figure out how old a structure is. More craters genuinely means an older surface.
That's so cool. Earth has craters too, though, right? So how does that connect to the ones in space?
Yeah, we do have craters, around 190 confirmed ones. Meteor Crater in Arizona, like you mentioned earlier, is a great local example. The most famous is Chicxulub in Mexico. That's the impact that caused the mass extinction that wiped out the dinosaurs a long, long time ago, 66 million years ago. We don't just like see most of Earth's craters because erosion and plate tectonics erase them over time.
That's awesome. So you've mentioned craters as being one of the big four areas of what astrogeologists study. What's another area?
The second biggest would be volcanoes. And it's not just an Earth thing, surprisingly. Mars has Olympus Mons, which is nearly 3 times the height of Mount Everest and the largest volcano in the solar system. That's right. Mars and other planets have volcanoes. One of my favorite examples, other than Olympus Mons, is Jupiter's moon Io. It's the most volcanically active body that we know of, just always constantly erupting. Even our own moon had massive volcanic activity billions of years ago. Some of the dark patches you can see on the moon from a telescope are ancient lava plains.
That's really cool. It kind of reminds me, I remember we were talking last week and somebody had mentioned that you could find the same sort of rock that you can find all around New Mexico because we're such a tectonically active area. You could find almost the exact same kind of rock on the moon, which I thought also really cool that it just kind of constantly mirrors. And so we've talked about rocks, but what about water? I feel like that comes up a lot in planetary science, especially in searches for life.
Oh, yeah. I mean, all the time. And for good reason, too. Because wherever we find water on Earth, we find life. So astrogeologists look for evidence of past or present water on other worlds. Mars is one of the biggest examples. It had ancient riverbeds and floods and just giant oceans and sedimentary rock layers that tell us liquid water flowed there billions of years ago. And several moons of Jupiter and Saturn, like Europa, have liquid water oceans under their icy surfaces right now.
That's really interesting because this ties in astrogeology with like astrobiology because we can see the interactions between water and stone. We can see the erosion it might create. And so I think it's a really cool link between astrogeology and astrobiology where they're so interconnected and we can see so much of one in the other. So we've talked about water, we've talked about volcanoes, and we've talked about craters. What's the last thing that is another really big area in astrogeology?
That would be rock and mineral composition. Basically, what is a world actually made of? This brings me to a good example of the rovers that we have on Mars. We have two that are still active. Curiosity, which landed a while ago, like 2012, I think, and then Perseverance, which landed in 2021. Both of them carry instruments to analyze rocks on Mars. But Perseverance was supposed to have a secondary mission that would launch from Earth a few years after its landing to also land Mars a bit a ways away from it, and Perseverance would load it up, this payload, this secondary rocket, with its own samples for that rocket to then launch off of Mars again and then come back to Earth to bring us the first ever samples of Mars. And with this, and this mission has had a lot of delays. I mean, we were originally planning for like a 2024 landing, I think, and it's 2026 now. I know Rocket Lab made a proposal to NASA for a lander. It's cheaper than a government plan. I know the original plan NASA had was a couple $1 billion and would have landed in like 2035, which is not ideal at all. Anyways, now with our new, or I guess semi-new administrator, NASA administrator, Jared Isaacman, he's been doing a good job at getting NASA back on track or just making things go quicker. So who knows, by 2030, we could have Mars samples. It just depends on time and budget, as usual. Bureaucracy, it's normal. So yeah, those were the 4 main things that an astrogeologist actually does.
That's really, really cool that we have like plans in the future to maybe have Mars rocks come back to Earth so we can study them.
Yeah, I mean, absolutely. But how can we study stuff that is very far away that we don't have the time or money or just the energy right now to send a real lander to a body?
Yeah, that's a great question, Wyatt. So, one of the big ideas, scientific concepts, and scientific fields that is used when studying other planets and trying to figure out what's going on other planets is spectroscopy. So, spectroscopy is the study of light, and the basic idea is that different materials emit and interact with different wavelengths of light, which is the electromagnetic spectrum, in different ways. And so, based on these set interactions, if we know the outcome, we can know what went on in the middle. So, we know that if a certain light is emitted, it means that light interacted with this element. And so, because of this, we can look at light emissions from basically anything, including planets that are super duper far away. And we can look at those and we can look at what they emit. And then we can figure out what elements are on the planets and figure out what molecules might be on the planet and if there's water or if there's oxygen. And so we can figure out all of these things about the planet just by looking at the light that it emits and how the planet interacts with light.
That is really cool. It's crazy that we can just do things like that. I mean, all of this, it's absolutely insane, really. Anyways, that's gonna be it for us today. But the next episode, season 2, episode 9, is going to be a really, really exciting one. We're going to be talking to science communicator Summer Ash for Reflect Orbital. It's a really interesting topic. You would not want to miss it. Anyways, I've been one of your co-hosts, Wyatt Wade.
And I am your other co-host, Pascal Heitzman.
And we'll see you on the next episode of the Space on Earth podcast. Thank you for listening.